trying to figure out if there's a center to the universe. And there's been different opinions throughout the centuries. First on what the universe is, and then on whether there is a center to that universe.
Well, that's a good point, because first you have to figure out what is the universe. Then you'll know. I mean, then the answer will be self-explanatory.
And a lot of it had to do with, unfortunately, all these people say we need to observe, we need to run an experiment. No, we don't, because it's experiment and observation which kept us back. See, they observed, and here we have Aristotle, right? And he observed, well, not only him, all the Greeks, they observed, right, with their eyes, right? They didn't have telescopes in those days.
You got to start somewhere.
Yeah, and so they went in there and they said, look, all we see is up to Jupiter, Saturn. Those are the only planets. They saw the first 7 planets. They didn't know anything about Uranus or Neptune or Pluto, right? And so they said, look, we have all these planets, and they put the Earth in the center, and they had even the sun rolling around, the Earth. Okay, this was their initial
geocentric.
Well, yeah, but the issue here is this was their initial idea of what the universe was like, because all they could see was the planets, and then you see the stars. They were so far away that they stood still as far as they were concerned. So they say, okay, we know what's happening here. Those are little dots that God stapled onto the firmament.
Yeah, the firmament.
And they're standing still, and we're rolling around. So this was their notion, because this was from observation. That's why you never have to observe. You have to shut your eyes, never see again. Blind men can be scientists.
I wouldn't go that far. I think observation, because again, even when you do this experiment, you're still observing the spoon go down.
No, because let me clarify that for
Clarify.
you. Okay.
Clarify. What do you get clarified?
Okay, I'm a blind quadriplegic.
Okay. Yeah.
Right?
Yeah.
Kind of like Stephen Hawking.
Yeah.
He was blind mentally, right? Okay, and quadriplegic, right? And someone comes to me and says, "Dear sage, we want you to enlighten us. We have this knife that constantly falls to the ground, but it never falls to the ceiling. Can you explain why?"
Why is he asking that?
I've never seen it.
I've
never seen it.
But you're going off of his observations.
Yeah, I don't care, but we don't even know if it ever happened. It's a hypothetical situation. It happened maybe.
It's suspiciously
asked.
Why that specific question if we're going
off? The kid says, I have a feeling that if I let go of stuff, it might fall to the floor. Can you explain why that would be so? I mean, they can phrase it in a way that nobody observed anything.
My point is, our questions come from our observation. We're not pulling questions out of our ass.
But again, observation does not give you an explanation.
No, I'm not saying that. I'm saying observation is what gives us our questions.
Observation gives us the assumptions.
No. Observation gives us our questions.
Which is part of the assumptions, because that's what you're going to answer with a theory. The explanation answers with the question.
Yeah.
In other words, it's part of
our assumptions.
hypothesis.
No, hold on. Our assumptions come from our other assumptions in a way. Somewhere down the chain, it ends up at our observations, obviously.
I guess you could say that, you have a question out there. Someone asked a question because they had maybe an observation. Yeah. But now the explanation, in other words, the theory, the part that involves science has nothing to do with the observation.
Okay.
It has to do with, let us make an assumption. And you make the assumption. What are the objects? What are the definitions? What are the initial scenes? And now you explain it. But it's based on, the guy observed it, but the observation itself is not part of the scientific method.
That's true, but there's another back door, which is the fact that the assumptions you usually use are based on another assumption or an observation.
This is true.
That kind of muddies, it makes it hard to do physics in a lot of ways, because you never know if those assumptions are correct.
No, but again, we don't care if there's no such thing as correct in science or right or wrong. What it is these are my assumptions. You have to take them at face value to understand my theory. It doesn't mean you believe in my assumptions, or you're just conceding them momentarily to understand what my explanation is.
But there's always going to be that part of you. I guess when I mean correct, I mean that when you say understand, the understanding usually it almost matches with correctness, because the understanding is basically saying, aha, it all makes sense. it all matches everything I've seen or been told how the universe works. It's like
And
that the understanding.
not necessarily, because again, observation. Sometimes we get fooled. The guy said, "I observed an angel." Well, did you?
Yeah.
I mean, what did you observe? How much drugs did you have?
But usually, when when you say understanding, which is kind of the goal of science,
yeah,
that's a loaded word because it's got a lot of observation. It's got a lot of assumptions, which both might not actually match how the universe works. Like he might understand something,
but the observation itself could be wrong. You may have observed something, or you thought you observed the ETs landing on your backyard. Well, did you? I mean, did you see? In other words, you're putting more into the observation than what was really there. That's what you saw. You think you saw, maybe. Especially on invisible things. When you have this, you say, "I observed particles pushing this down." Well, did you observe the particle?
Yeah.
I mean, you're already giving me a theory.
That's what I'm saying. I don't think it's easy to remove observations and, I guess, corrupt assumptions, for lack of a better term. By corrupt assumptions, I mean an assumption that you have that not just doesn't match reality. That's not what I mean. I mean it's an assumption that you heard from someone else. Like when we're talking about atoms, no one's ever seen an atom, so you dispense with the word observation, but it's an assumption that we have based on other assumptions, based on other theories. So it's like this chain of, like, all the assumptions we're using to explain things are basically taught to us. It's not things we've seen.
Yeah, but again, you're talking about, for example, seeing, observing, right?
No, I'm not saying that.
No, hold it. But let me just look at this. When we look at the universe, there are many things that are so far away that even with the satellites that are out there with great telescopes and whatever, there's too far away anyways, and you say, well, what did you see? Well, I saw a light, and this is what I think it is. So you have a theory. Now, the other guy takes that theory and uses this as an assumption. Yeah. Well, you can. There's no problem when doing that. You're taking that as a given to understand his theory. Yeah. But you say, I have a different theory, and for that I make a new assumption. I'm saying that your assumptions of what you think you saw was wrong. Yeah. And so, again,
here's an
that's why I'm saying that observation is not part of the scientific method. What is part of the scientific method is that you're going to make some assumptions about what objects are out there. You're going to make another assumption about your definition, what you think, how you're going to define these words, how you think they should be defined in a way that you can use them consistently, scientifically. And then you have the initial scene. Again, you put that into, you're the prosecutor of your theory. Yeah. You're going to put all that the way you think it happened. It doesn't mean that that's the way it happened, or that I agree with your assumption. I have a different set of assumptions, but I'm going to listen to you. I'm going to concede your assumptions only to understand what your theory is. Okay, so we have to distinguish observation and an experiment that you ran and what you think you saw from, the scientific method, which says, I'm going to make an assumption about the objects, especially the invisible objects. I can't observe, the mediators, so I cannot talk about an observation here. I can observe what I can see, the knife falling, but I cannot observe what caused it. And for that, I have to make assumptions.
Well, here's a good example, just in our conversation. Sometimes we'll, in fact, very often, we'll take, like, the slit experiment, or no, because slit experiment we can do at home, but we'll take some experiment that someone has done at, like, the Large Hadron Collider or something that's extravagant, and we'll try to explain what they think they saw.
Right.
So we do that kind of thing where it's like, okay, we are trying to match reality testing, even though the testing may be false, even though what they think they saw might be wrong. Something happens, and it's one of those things that it almost begs a question. Like when you see planets going around nothing, that's an observation, which begs the question, what is going on there? So that's
put the black hole in.
Yeah, that's the thing. But whether you put a black hole or magnetism or whatever it is, you put something in there to explain it. It's almost like observations beg questions.
Yeah, but the question is, you observed the sun or the star going around something. You did not observe the black hole. You did not observe the magnetic field.
But what I mean is, there's always some observation that creates the question.
Yeah.
That's all I'm saying.
But that's why I'm saying that part, the observation part, should be outside of
The explanation.
In other words, outside the scientific method. The scientific method should only include, look, these are the objects, especially the ones we see. Then you make an assumption about the objects that you can't see or touch, and then you get the definitions and the initial scene. Now you explain what now you try to explain the answer, or give an answer to the question.
Just to cut this off, the last thing, one thing you could even do is the explanation could just beg the validity of the observation. Like if I was high and I saw the devil talking to me, why did I see the devil? Well, you were high, so you were seeing things. Yeah, it's like that's the explanation. Is your observation is off. What you saw, what didn't match reality, essentially.
Okay, so here we have Ptolemy, and he made a modification of that. He took the epicycles and he put them this is what the Greeks in general thought. They thought that the planets were rolling around some kind of ring. And so this was their notion of the universe. They only had, 7 planets, right? And that was it. So this is what at least we inherited from the ancients up to 2,000 years ago. And then after that, you had what we call the Middle Ages, the Dark Ages, whatever they want to call them, right? And these folks essentially, just took the Greek stuff and just memorized it and passed it on to us. It wasn't until the 17th century, or really here in this case, the 16th century, you have Copernicus, right? He comes in there and he says, oh, look, really the sun is at the center and not the earth. And all these planets, right, they go around. I don't think he mentioned anything about stars. He was more concerned about the planets. He wanted to explain that, the earth is at the center and not the sun is at the center of our solar system, not the earth. So that was the big break that we got there, a change in, you could say, the new paradigm, okay? And you had one fellow about 100 years later from Copernicus. His name was René Descartes, French guy, and he did it with his vortices. He started having the planets move around in vortices of some kind. So exactly how he imagined it, I don't know, but this is the way I imagine his imagination.
Okay? I like that.
Yeah.
Spinning.
Okay, so he had the planets. He says this is where the planets move around because they're caught in vortices. Okay, he had this notion of vortices, and he believed, like Aristotle, that there is no such thing as empty space, because as soon as something comes out of that location, something else fills it. That was the notion they had. So it's like there's never a moment in which there is an empty space. But the question is, that location that the guy left, the position he left, what is that? What is position? What is location if not empty space, right? Okay, a few years later, we have Newton, and he comes up there and he has a different notion. He starts saying, look, is the universe finite or infinite? And he says it cannot be finite. And then you say, well, why not? Why can't it be finite? He says, look, you have this finite and bound universe, right? All the stars would what? Fall down into the middle of the whole of space, and they compose one great spherical mass. He said if it was a finite universe, gravity would pull them all together to a point. That was his notion. So he said, no, the universe has to be infinite, because then at that point, you don't have any center of mass, or essentially everything on the outside pulls in different directions, and so it's not all pulled towards a single center. And so he says the universe cannot be finite; it has to be infinite, whatever that means, right? Because again, infinite is infinity. These are words from mathematics. And he says infinite universe, the gravitational pull from all sides is balanced out by the pull from the other side. You have stars and galaxies and whatever pulling from every angle, and so it doesn't condense in a single center because the universe is infinite. Okay, only if it's finite then we have a problem, right? He says the fixed stars being equally spread out in all points of the heavens cancel out their mutual pulls by opposite attractions. He was saying that there's gravity works a little differently out there, in a sense that it's not always inwards, but over there's a pull in the opposite direction. There's gravity, but in the opposite direction. So everything's not pulled towards the center. And he says it is impossible to have a infinite static model of the universe in which gravity is always attractive. Okay, that was essentially his conclusion.
Lack of imagination.
Well, here it is. Let me show you. Here's the universal collapse. Okay, this is what he was thinking. He's saying if it's finite, we have a problem because all the matter would be drawn inwards by gravity, and we would end up with a mass in the center, even if it's spherical. Right, which I guess that's how he imagined it. It can't be. He says it would all condense into a point. That was the problem he saw with that. So he said, no, the universe has to be infinite. But the question is, what is infinite? What do you mean infinite? What does infinite mean? There's no such thing as an infinite object. If the universe is a thing, an object, what do you mean infinite? Is space infinite? Or is the number of objects like planets and stars and atoms, is that which of the two is infinite? And what do you mean by infinite? Infinite just means that it's incessant. If you travel incessantly, you would never reach an end, even if you were eternal, right? So that's what he's saying. Okay, so you got to define the word infinite if you're going to say the universe is not infinite or is infinite. In his case, it was infinite, right? And
I think most people would say
here you have
infinite.
You have the infinite universe, okay? That's what it looks like. It just stretches out beyond the borders of what you see there.
Most people would say the universe is infinite without really giving it much thought.
Yeah, but because they don't know what the word infinite means. Infinite is a word that belongs to math. It's got to do with numbers. The numbers are infinite, meaning, what does that mean? Is there a last number? No, it means that you can count incessantly. That's what infinite means. So it's really an adverb. It's not an adjective, right? There's no such thing as an infinite object. All objects are finite. That's the definition of the word object. That is a synonym of the word object, finite. So there's no such thing as an infinite table or infinite rock. What do you mean by an infinite rock? It means that I go incessantly, I never find the edge of that rock, a surface. You know, that's what we're saying.
I think when most people say the universe is infinite, they're just really saying it's vast. I don't think they think more
beyond
that. It's like it's really big.
It's big.
It's big, yeah. I mean, when you have imagine if you had like an airplane that was like as big as a country, most people would say this is an infinite plane. Like, where's the end of it?
Yeah.
It's freaking huge.
And part of that is not so much, I mean, you could say that the stars also, they say, well, I look and everywhere I see it, there's stars. But I think it's more related to space itself. They say space, where does space end? And everybody say, well, it's infinite.
Well, it also sounds weird thinking of an edge of the universe. Like, what?
Meaning the edge of space.
Well,
that's what you're talking about, really.
Well, yeah,
they say universe, but they're referring to space.
There's the edge of the matter in universe, and then there's the edge of the black spaceness, whatever that is. And it's like, okay, well, what's beyond that? What contains that is always the question.
And here you have one guy, his name was Olbers, okay? He comes with the paradox, or why is the night sky dark if the universe is infinite, right? And this is his reasoning. He says, there would be an infinite number of stars in an infinite universe of infinite age, okay? Universe must be finite. Why? There is a center of gravity from which all stars are pulled. Your line of sight should eventually hit on a star's surface, no matter where you look in the sky, right? Every direction would lead to a star. The night sky would be infinitely bright. In other words, we should see every star in the universe. And that is clearly not the case. We see some stars, and between them we see some black stuff. That's what we see.
Starlight is absorbed?
Yeah, and so this was the counter-argument. The counter-argument is starlight is gradually absorbed while traveling through space. This cuts off the light from any stars beyond a certain distance. So they said, we can explain that. The light from some stars hits something and doesn't reach your eyes. That's why we see black stuff between the stars. And the counter-argument to that said, any absorbing gas or dust would simply heat up until the starlight is it had absorbed would be radiated. In other words, whatever object is there would heat up, send you the light anyway. So you still should see the whole light sky lit up, right?
Did they have the theory of tired light at that point?
It's around that time that the tired light thing started, the debate over tired light came into being. And it says, so there you have it. It's a re-radiate. The energy we would detect as light from the earth would be the same. So let's understand that. What Olbers was saying, And that's why they couldn't really figure out if the universe was finite or infinite, because you got to determine that before you talk about the center, right? That's the issue. And so if the universe is infinite, they said, well, all these stars with infinite stars there, we should be blinded. We should, everywhere in the sky at night, we should not see night. We should only see light. We should see all this light coming into our eyes. Why don't we see it? Well, some people say, well, you got all these gases, you got all these planets, and they're in the way, and so the light from certain stars hits them, and that doesn't reach your eye. And the counter argument to that was, well, yeah, but if that light came in, it heated up the object over millions of years, and now that one is going to irradiate light to your eyes. So it's not like it's a wall. It's just a relay race. You know, they relay it to the planet should relay it to your eyes. Those were the arguments that were kicked around.
What's the second law of thermodynamics?
That energy is constant. You know,
doesn't that, if you believe the energy is constant, that there's no extra degrees that gets created anywhere, wouldn't that cancel out infinite universes? Infinite matter?
If you would?
Because if the amount of heat in the universe is constant, because that's essentially what the second law is saying, which they all believe in, wouldn't that basically cut off any infinite universes? Because infinite matter, at least in a universe, would mean there's stuff being created. Which is
why are you saying it's created? Let's assume.
Well, what does infinite mean? It means there's another one being made. There's another one being made. But that means that's changing the amount of degrees that are in the universe.
Well, that's what I'm saying. The word is incessant. Incessant
but
creation of new.
Incessant creation of new. But creation of new means that the energy in the universe changed.
Right. And so you have that.
Whatever energy is. I'm just using degrees as a nice, more grounded.
If you're going to create it with a magic wand. Right? Then they say, well, whatever, once energy exists, once the matter exists, mass, energy equals mass times velocity of your light squared. Once you create mass and energy, it's there, and now you can't make it disappear. Because the issue with energy is you can, they say it cannot be created also. So, I mean, they do whatever they want. They say it cannot be created or destroyed. Well, here you're saying we can create it, but we cannot destroy it.
I like the second law of thermodynamics. I think I'm going to keep that one.
Yeah, okay, so here we have Einstein. He comes up, and he also tries to answer that question, is the universe finite or infinite? And he says he comes up with a finite, unbounded universe.
Oh, I mean, that was close. That sounds good. I like finite, unbounded.
Yeah, but the problem...
Finite, unbounded to me means the matter is finite and the black stuff is unbounded.
No, what they're saying is something else, as we're going to see. The unbounded means you walk around it. Right. Unboundedly. That's what they mean. But here it is. He says the three-dimensional spherical space, he's assuming it's a sphere, right? And he's talking about space here, okay? Is quite analogous to the two-dimensional spherical surface. It is finite, in other words, finite volume, and has no bounds, okay? So he's saying it's finite, but hasn't, like a ball. Here you have a ball, right? Let's get a little ball here. Here you have a ball. It's finite. And you say, what do you mean it's unbounded? It looks like it's bounded also. Bounded meaning it's got a surface. It stops here, right? Bounded. But that's not what they're referring to, as you will see. They're talking about now motion around the ball. That's what they're going to refer to. And so he says, since in reality, the detailed distribution of matter is not uniform, the real universe will deviate in individual parts from the spherical. In other words, he says it's more or less spherical, but it's not perfectly spherical, right? The universe will be quasi-spherical. Okay, so it's more or less spherical, or tending towards spherical.
It has a topology,
but it's not completely smooth. That's what he's saying.
If you zoom out, it looks like a ball.
But then he says,
it looks like
but it will necessarily be finite. That's important. It's finite, like this ball is finite, right? Okay, so he's talking about a couple things there. Let's look at both of them. The first one he says is, here's the AI. He gives us the modern version of what Einstein essentially was suggesting. The AI says, modern cosmology, right? We always know, right? They know. Okay, we know that the universe is either infinite or finite. Well,
that we do know. That we do know. Hey,
there's no gray.
The AI got it.
It's not
it.
Semi-finite.
No. It's either finite or infinite. He's right
It says,
about that.
but unbounded. Where did the AI get that? Well, you trace it to Einstein. And it does not have a center. So if it's finite, how come it doesn't have a center? I mean, you would think that here's finite, the finite ball, and it has a center. Why doesn't the universe have a center? And now we're going to find out in a minute, because that's what they were trying to figure out, right? Okay, so here, let's move ahead. And let's go first with Stephen Hawking. 100 years later, he comes up with the same thing as Einstein. He says the finite, unbounded universe. And he said the universe is not infinite in space, but neither does space have any boundary. Now that sounds like a contradiction, because if the universe, meaning space, is infinite and it doesn't, but it doesn't have a boundary, what do we mean? Either it's finite and has a boundary, or it's infinite, extends forever. I mean, what are we talking about? There seems to be a contradiction. It says gravity is so strong that space is bent around itself, okay, like the surface of the earth. It is impossible both for space and time to be finite without any edges or boundaries. Yeah, okay. If one keeps traveling in a certain direction on the surface of the earth, now listen to this, right? One never comes up against an impassable barrier or falls over the edge. So he's talking about motion around the ball. That's what he's talking about with unbounded. So you see, he's talking about two different things. He's comparing apples and oranges, or worse, apples and boundaries. No. Here you have finite on the left, and what you see is the earth, right? And it's finite, it has a surface, and that's where it stops. So yeah, the earth is finite. What is unbounded? Unbounded means that you won't find a fence if you roll around it, which has nothing to do with the finite part. That's still finite. But they say it's unbounded, meaning you can run around forever.
Who cares?
It's got nothing to do with what we're trying to answer. The question is not.
Is there a center to the thing that you can run around?
Not only that, is the universe finite? If it's finite, I don't care if you run around it; it's still finite.
Yeah,
you can't say it's
forget
infinite.
the unbounded part.
But they say, and so you say, well, then we have a problem, because it seems like you would think again that you can find a center in a ball, right?
Yeah,
it's got a center. They say no. There is no center.
Okay, there's no center to
And let me show you how they came up with that one.
Oh, boy. Here we go.
Okay, so first they're going to answer Olbers. Again, Stephen Hawking, he says, the universe began some 12 to 15 billion years ago. The universe is not old enough to fill the night sky with light. So he's saying that's the only issue. The light from some stars has not reached us yet. That's why you see still black stuff between two stars that are visible within our observable universe, right? That's what he's saying. While the universe may be infinite in size, there has not been enough time since it first came into being for starlight to reach us from the farthest corner of space. So what he's saying essentially is, there are stars everywhere. You should be blinded, but some of those stars are so far away that the light has not reached us and may never reach us, because they're receding from us at faster than the speed of light. So this is what they're saying. We see a part of that lies within 12 to 15 billion light years from us, with the rest of the stars beyond our sight. The number of stars whose light reaches us is not enough to fill the sky with light. Okay, that's what he's saying. Clear? Straightforward? Okay, so he's saying the answer that they have today is that
universe isn't old enough.
One, it's not old enough. Light is not fast enough to cover the ground that from the spatial expansion, the expansion of space-time. So space-time is expanding faster than light can reach us from some of these stars, and that's why between any two stars you see darkness, blackness.
I love when you're trying to explain their theories when you just casually use the words expanding space-time.
Yeah.
Like it means something. You just use the words like they do, but what?
What does that mean?
Yeah.
What's expanding is the number lines. The number lines expand very fast. Okay, so here he says, here he shows, he says, the Big Bang was not an explosion in space, but an expansion of space. In other words, space itself is expanding. It's not that, you have an explosion within space. So the black stuff there, that's the one they never identified, never will, because space is within the ball there, not outside of it. The black stuff is not space, and they never identified what physical object, is outside of space-time. What is space-time pushing up against? And you say, well, it's an irrational question, blah, blah, blah. We have multi-universes. That's the next thing that they propose, that there are many universes out there. What's between the two universes? That's all you got to answer. Very simple. What's the stuff between the universe if the universe contains, each universe contains space, time, and matter? So what separates it?
Once you get to the hard questions, you pull this thing out.
The magic wand. Okay, so here we have it. And so he concludes that the universe has no center. Okay? And here we have it. Here's the relativity. This is why there is no center. They say the center was when we started out, the Big Bang. That's that little dot in the center. That's the Big Bang.
Isn't that the center, though?
No, not anymore, because the universe is only the rim.
Yeah, because they're saying the universe is just the tapestry, the edge, the rubber of the balloon.
Right.
Whereas the center of the balloon wouldn't be part of the universe.
Right. You got it. The center is not part of the Big Bang.
In fact, the center isn't even part of time, because time is also the part of the rubber of the balloon.
And then again, they put a loaf of bread and they start at the Big Bang.
Yeah. Okay, I got it. I'm just.
So they have all these contradictions, these misconceptions.
It's because they play around with time and location
when they need it.
They're saying, when they need it. There's no location in there.
It's all ad hoc, And so how do we explain all this? Well, here we have our universe, okay? This is how we started out. There's your universe. We think it's, again, it could be like a ball. Here we show a cross-section, you could say, of the universe, okay? So we show a little plate or a little disc, but think of it as a 3D ball.
This is the rope hypothesis.
Yeah, but now we're going to interconnect it. Remember, under the rope model, all atoms in the universe are physically interconnected. So here we show some interconnection just to illustrate that all atoms are physically interconnected, okay?
So it's more like a ball of yarn?
Yeah, essentially.
With a lot of space in between the yarn.
What you have is interconnection between atoms. That's what we're illustrating there, okay? Okay, so, but our universe rotates, it spins, okay? So there we have it. The whole universe spins. And the question is, why don't those stars at the edges fly out?
The universe spinning is my money as to why it's flat. But continue.
Okay, it could be, and that's why we illustrate next. Here you have the
flat
universe.
By flat, I just mean not a ball.
Here you have our flat universe.
Like, it might have some height. I'm just saying it's not a sphere.
I don't think it's flat. I think it's more or less spherical, but it could be like a pancake, somewhat like a pancake.
Yeah, my money's on pancake.
Okay, so no problem. That's you can make that assumption. Okay, but here you have our universe. Now remember, what we're going to do here, we're going to interconnect all the atoms. So remember, what you have here is the following. Here, let's see if I can illustrate it. Here it goes. We have our spider web, and we're going to put it into the universe, into our flat universe.
Carousel.
Yeah.
Oh, I like that.
Yeah, so what we have is all atoms are interconnected, okay? So the universe rotates. Here we see it from the side. We're assuming it's a plate of some kind or a disc. Doesn't necessarily have to be like that. That's just one assumption that you can make, okay? But they're all interconnected. So there we have the spider web, so that you know all atoms are interconnected, all stars are interconnected, physically interconnected, not connected by consciousness or anything like that, energy or any of those nonsense. No, they're physically connected by ropes, electromagnetic ropes, and the whole thing turns around, okay? So that's what we're illustrating there. Okay, so that's our model. It could be a spherical model, right? But it gets a little more complicated when you try to illustrate the spherical model for what I'm going to show next. Because now, we're going to, on top of that, we're going to put the magnetic thread, the electromagnetic threads that are spinning around. So you have the universe, it's spinning around, but also we have all the threads that are spinning around the entire universe.
Yep.
What does the edge of the universe look like? If you had the eyes of God, it would look like the electromagnetic threads swinging around the entire universe. And within that, I don't know if this can show you in any better way, but every galaxy within the universe also has, the threads spinning around them. So we have threads within the galaxies, and the entire universe is rotating, and you have the electromagnetic threads kind of giving a little bit of structure to the universe. Remember, the reason all the stars in the edges do not fly out is because they're all attached.
Can I ask a Pops question here?
Okay,
what's the black stuff?
Black stuff is called space. There is no black stuff. It's black or dark or colorless, or it doesn't emit light, whatever you want to call it. The black stuff is what we call space. And space is not infinite, or nothing. And space is that which does not have shape. Okay, that's what it is. So the black stuff is a contrast that we have to matter. But there is no such thing as black stuff. The black stuff is simply nothing. And what is nothing? That which has no shape.
Nothing is a confusing one, but we don't have to go deep into it. Nothing will suffice. Because everything you just said is a lot more than when you ask that to a mathematician as to what is the black stuff, or what is the stuff between the blacks. If the black stuff has an edge, what comes after that, etc., etc.
Well, remember, you have to make sense of the language, first of all. And so we say...
but nothing's a weird one.
Okay, no, it's not. Not so weird. Listen,
weird. Maybe no matter what words you use, it's always weird.
No, let's show you that it's not. There's something called an antonym in language. What is an antonym? It's a type of word that is totally the opposite of another word. So we have something, and this is a something, for example. It has shape. And then you have nothing. What is nothing? That which doesn't have shape. They're opposites, they're antonyms. Now we can use them consistently, scientifically, rationally. And that's the issue there. All we're saying, you have to define words in such a way that you can use them consistently. That's where the mathematical physics fails completely, utterly. They've never defined what space is, what nothing is, what something is. They don't have any definitions for any of these words. They say something is that which you can see or touch. So is the table that I can't see or touch, is the table I'm thinking of, is the table you're thinking of that I can't see or touch, is the word table referred to an object? Yes or no? Why is it an object? Because it has shape, not because I can see or touch it. So again, they're using all these, or they say what it's made of. Well, the table that's in my mind is not made of atoms. The table that I eat my breakfast on, yes, but not the one I have in my mind. Or those are not made out of atoms. Or the one I drew, those are not made out of atoms. Okay, the one that's made out of atoms is only the one I eat on, and that doesn't mean that a table is not an object. A table is an object because it has shape. And something means that which has shape, nothing that which doesn't. Now we have consistency in the usage of our words. And that's what the black stuff was, nothing.
Yeah, I like the long-winded answers to a simple question. Yeah. That means you've thought about it a lot, too much, probably.
Okay, so here we have one question that might pop in the minds of people. And what if you wanted to leave the universe? Okay, so here you have the universe. It's all interconnected. But you take your spaceship and you're trying to get out of the universe. You want to go to a different universe or whatever. You want to get out of reality, okay? Can you do that? Or will the mass of the universe pull you back? In other words, all the ropes are connected to you under our version of the universe, right? And the question is, will all those ropes prevent you from leaving, from being a free, escaping prison?
Worse, the magnetic waves, basically, that make the universe basically more like a donut, would also sweep you back in like an ocean, I think.
Yeah, because remember, the universe is rotating. Yeah, I didn't put that in there, but...
Not just rotating, but I'm talking about the magnetism that sweeps.
Oh, the sweeping, the sweeping threads that sweep
around. Because you just drew the matter, not the threads. Right, but if you added the threads, you would also have threads that are pulling you back. Here, this person is basically fighting against the gravity of the whole universe and the sweeping threads that were sweeping. So it's so impossible.
Yeah, I mean, even God can't get out of here. He doesn't have enough strength to leave the universe. So there you have it,
What
folks.
is the escape velocity of the universe?
Hold it, but let's answer the question. The question is, does that universe have a center? Of course. Whether you see it as a plate or a disc, or whether you see it as a ball, a sphere, that it has to have a center. Because what we're saying is, in case of the ball, right, that this is our universe and it has a center. That differs from the general relativity universe, which is a shell, right? They say, look, there's been an explosion and all the matter is stuck around the center, around the edges. It's like he said, the rubber in the balloon and not the air that's in the balloon. Yeah. The problem with that is that they take their telescopes and they say, we're going to try to find the origin of, we're going to try to see if we can find the point where space-time exploded, the Big Bang. But that's in the center. You're trying to look for a center in something that doesn't have a center according to general relativity.
Can't they just aim down?
No. The point is, you can. What they're doing is sending their telescope sideways along, the rubber of the balloon, and they're saying we're trying to locate the Big Bang that happened in the center 14 billion years ago.
I feel bad for the astronomers. Every time a physicist comes and says, hey, can you look for something from me? No, not again, man. You got me looking for invisible black holes. You got me looking for centers of universes that I can't even look at. Like, where do you want me to point this thing? What do you...
So that's it, folks. Yeah, under the rope model, there is a center of the universe. We don't know where it's at. Don't ask me that because I haven't seen the entire universe. Ask God. He's outside the universe. He can see the whole universe. He'd say, look, the center's here, okay? So if you have contact with God, please let him send me a letter.
I would say it's fun to speculate because we do have, given our assumptions that we've crafted over so many years, we do have ideas of what the center and the edges could look like. Because again, we're talking about when we talk about the teardrop atom, when we say all atoms are interconnected, usually when you draw a hydrogen atom, the simple atom, you draw an urchin, spike ball. But when we're talking about a hydrogen atom
on the outside,
yeah,
on the outside it looks like a
when you're talking about a hydrogen atom at the edge, there's no ropes coming from the other side, so it looks more like maybe not a teardrop, but like a half circle. It's like this weird, and that just gets weird because I'm assuming the laws of physics as they are, get really weird in the reality of the edge of the universe. I would bet we're not in the edge of the universe or else we'd see some weird shit.
Well, if you're in the edge of the universe, what
give us a call.
No. The edge of the universe is swept by threads.
Yeah, I'm not talking about
no matter.
Okay, I'm not talking about the edge of the sweeping. I'm talking about the edge of the matter.
Okay, the edge of the matter.
That's got to be some weird.
We should always make a distinction between universe and matter.
Yeah.
Okay, and that's one of the things that.
Well, that's also confusing when they talk about space.
Right. That's when you talk about space-time. The expansion of space-time includes what? Space, time, and matter. All three of them. So they say it's all expanding. No, matter does not expand. It's blowing apart. You could say that space is expanding, but not matter. Matter is just blowing apart. And so they use that word expanding for both, and that's very confusing.